Hello everyone. So we're going to do a third video. This is conduction and radiation. I'm going to do these two, upload them, and go to bed. The cats already are encouraging me to get there. So just a reminder for conduction, all right, our formula looks like this. All right. And of course the white balance is atrocious there, but that's okay. So, K here is a thermal conductivity. It's a thing you look up. I've got a table of it here from OpenStax. Alright, and it's in units of watts per meter degree Celsius. And you'll see here they also show writing it as a derivative here, so you can calculate at a particular depth in a material what the temperature might be for a given power out. Right. So we have this formula, and we can do this sort of simple problem where we have a person and they are in a wool coat. Right, not a very good wool coat, but we can model it as sort of a big container, right? And its thickness will be 2 centimeters, which is 0.02 meters, and its area will be 1.4 meters squared, right? And then you imagine a big woolly shawl or a blanket, and you wrap it around you, and it's going to keep the cold at bay, right? And so our question here in the problem is if 50 watts leak out, right? So there's a hot side and a cold side, and 50 watts are going through it. Can we figure out what the temperature change is? Right, and that might tell us like what the weather is, because we know what our temperature is. So normally we might do this a little different. We know what the temperature is and ask what the power is, but this is fine. We have 50 watts leaking out. Alright, so we can look at this formula and we're like, well, I want to solve for delta T, so delta T is our power times our thickness divided by our conductivity times the area. Alright, now one other thing we need here is a conductivity. If I go back to that lookup table, it goes on down through here, and we see wool is 0.04. Alright, so we'll have our wool is 0.04 watts per meter degree Celsius. And now we have everything. We can plug in everything that we need. Alright, so we'll have 50 watts. And our thickness 0.02 meters, and we can divide by our conductivity 0.04 watts per meter degree Celsius, and multiply that by our area 1.4 meters squared, and we can calculate that all out and get a delta T. And I got 17.9 degrees Celsius. So remember that a human is going to be about 37 degrees Celsius. Right? So this should be, right, the difference in these, the environmental temperature should be about 19.1. No, that can't be right. This is almost 18. No, that's right. Yeah, okay. Yeah, we're right. It's 18. Add these two, and we should get 31. Okay. Sorry, 37. So the other thing to think is, well, what are these temperatures in numbers you might be comfortable with, right? Well, this is 98.6. That's popularly known. This, very nearly room temperature. It's a little low, so we're thinking 65 to 70 degrees. Yeah, it totally seems... I'd totally rock a wool sweater at that, if I looked good in it. So, this is, I have one layer of material, right? Our model is, I have a layer of material, it has some thickness L, and heat goes through it like that. So we can ask the obvious question is, what do we do when we have two layers of material and L1 and L2 and some power goes through it? And what we note is a couple of things. What power goes through here has to be what power goes through there. So in a more complicated problem, you're going to have some additional unknowns, and all right, if we're trying to solve a hard problem, we want to know how to set that up. Luckily for you, I didn't assign that on the homework, so I just kind of want to take a moment and outline what that looks like. All right, I can make the problem go away for a minute. All right. So if we have two layers, right, we have K1 and L1, so the thickness and the conductivity for each one, and another layer, K2 and L2, and both of them need to have the same area, so A1 equals A2 equals A. If that doesn't make if that doesn't work, then we have some other problems, like why is the areas not equal? But if that's the case, then whatever power goes through this first layer has to equal what comes out of it through the second layer. Alright, well, the simplest thing to state is that the heat, the total heat that comes out has to be that. But it's also true that the rate has to be the same. So the power that passes through is equal. Right. So we can write these out. Right. Now there will be three temperatures here. Let me get a red pen here. There'll be a hot side. There'll be a cold side. And there'll be an interface temperature. Hopefully those are readable. Boy, the white balance on that is atrocious. All right. But what we can do is solve for this. And you remember, I made a graph. I looked like this, and it was distance here, so x, and then temperature here, and going through these materials, it should look like there's a distinct knee here, or it could be the other way around. It could be that this material has the low slope and this one has the high slope, right? But if we're trying to set this up, we're just going to use these numbers. All right, so we'll do K1 over L1 A T hot minus T interface, and on the other side, be careful here, this is L1, not the number 4, L1, K2 over L2 A T interface minus T cold. All right. The heat's flowing from the high temperature to the low temperature in both cases. And this is essentially two equations, two unknowns. I know this P equals this P equals that, and I know that they're equal, so it's kind of over-specified. So the trick is, once I know this is true, I can write this, and then I can solve for this intermediate temperature, and then I can plug back in and get the power if I want to. So it's important that if you're trying to do something with multiple layers, you realize each layer gets its own equation like this. And I want you to note that I separated these out a certain way, right? I separated them out, K and L are separate and K and L are separate. Turns out that it's really useful to think of the inverse of this, L over K, for a material. And this quantity is what's called the R value. Now, of course, when you buy insulation at the store, you are buying it in horrific units of British thermal unit per foot degree Fahrenheit per foot. Right, that is a horrible unit, but that's you're buying it, and it's going to be this weird flipped up unit that also has weird British or American units in it. But this is really nice because when you think about what's going on in a problem, all right, if I increase the thickness of my material, if I make L larger, L's in the bottom of these formulas, so the power is lower. The rate at which the heat leaks out is lower. If I make the conductivity higher, well, that's in the numerator, and that's going to make the power leak out faster. It's in the denominator here, it's going to make the R value lower. So by writing it like this, we're saying for everything a larger number is better. In context of insulation, a higher R number means less power out. So the other nice thing is that if you write it like this, and then you try to treat this thing as one single layer of one material, you can write your R value is R1 plus R2. Or your power out is A delta T over your total R value. Right? And that'll be, L1 over K1 plus L2 over, and that becomes a really weird 1 over fraction, but this is a nice way if you're designing something like insulating a house and you're just like, well, I need to minimize this number, then I want to maximize my R value. So it means you buy thicker insulation or you buy better insulation, better a lower conductivity, something like that. That's enough rambling about insulation. I want to go back to this sort of setup where we're talking about someone who is conducting energy to the environment and there's a temperature difference. We're going to look at the case where a person radiates. Right. And so we want to look at radiation. And so for radiation, the power is E sigma A T to the fourth. All right. And what I want you to know, T must be in Kelvin. And then this E goes between 0 and 1 is the emissivity, which is how absorbing or how reflecting. Right? 0 is a perfect mirror. 1 is a perfect black body. Humans are 0.6, 0.7, but for what we're doing, we can probably just neglect that. We can say that humans don't reflect light. I mean, obviously you see them, so they do reflect something, but it's perfectly reasonable to ignore this for what we're doing. So we're going to have a person. Their area is 1.4 meters squared. We'll take E equals 1. Sigma here is a constant. And, this is a universal constant, so it's on your formula sheet. And if you pay attention to your units, then you'll note, oh, I have Kelvin here, I must have Kelvin there. Whereas when we did conduction, right, I had degrees Celsius in my conductivity, so I could have degrees Celsius in my delta T. That was fine. All right, so I have to be a little careful when I do units on this stuff. So, you know, we're at the end of the last class we had. We're talking about radiation. What I want to look at is how much energy is this person absorbing and how much energy are they radiating. And we'll do the radiation first. So when they emit at a temperature of 37 degrees Celsius, which is 310 Kelvin, right? You add 273 to that. So when we want to calculate the power out, we'll have 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. We'll have 1.4 meters squared for our area, and then we'll have 310 Kelvin to the fourth power. And I'm going to come over here and I'm going to point out a calculator. There's no fourth power button on this, right? There's a square, there's a square root. Your calculator probably combines those two. If I'm going to do 310 to the fourth power, well, I'm going to square it, and I want to square it again. All right, it's 4 is 2 times 2, and so it's a thing squared and then that thing squared. And if I want to take the fourth root, like say I want to know the temperature, and I know the power, and I do this calculation, now I got to take a fourth root. Well, that's 2 square roots. So if you can remember that, right? If you can remember fourth power is 2 squares and a fourth root is 2 square roots, that's nice. Otherwise, learn how your calculator, and you've got a graphing calculator probably, learn how it does those fourth roots. All right, don't be... Oh, this does have an arbitrary root, so I can do 310. So I can get a big number for 310 squared and squared, store it in memory, and then I can do 310 raised to the fourth power, and I get a big number, and if I subtract off what's in the memory, I get 0. So I know it's the same. This will also let you do fourth roots. It's the secondary function. So if I recall that big number, oh wait, I can't do it. So, big number, I want to take the fourth root, shift. Usually there's some function like that on a calculator, and I'll get it. Right? So, know how to take an arbitrary power or an arbitrary root. Right? Figure out how to do that in your calculator. That's neither here nor there. We have this calculation. I need to run it. We can already estimate this is going to be, 10 to the 9. This is going to be on the order of about 10 to the 2. And when I run this calculation, did run it? Yeah, there it is. It is 733 watts. And there's some more digits, but that's close enough. Now, going the other way, right, we're absorbing, right, so here's our person, and they're emitting light, then this power is a function of being at 310 Kelvin. That's 733 watts. The power that's radiated is always based on the temperature of the radiator. So when they absorb light, well, it depends on where it comes from. Well, that's your environment. And if your environment's, say, 20 degrees Celsius, which is 293 Kelvin, right? then that's going to be a lower number. You're going to absorb less. All right? And if you do that calculation, the input power, how much you absorb from the environment, is, all right, because that's the trick, is you're not actually making this much power, like living. You're just, that's what leaks out of you. You absorb some more back in. Well, the power that comes in is going to be based the same calculation. I'm just going to write sigma instead of this long number, and the area, and then 293 Kelvin to the fourth. This ends up being 148 watts. All right. So the power at 293 Kelvin is 148 watts. And there's nothing special about these numbers in the sense of it being a person. Any object at 310 Kelvin and 1.4 meters squared and emissivity 1 radiates that much energy. Anyone at 293 Kelvin at those same values radiate 148. So this lets us get the net power, which is the difference. And I didn't actually calculate that. So 733 minus 148. I did calculate, I just didn't write it down. So the net power is the power out minus the power in, which ends up being 585 watts. So what does that mean in terms of the energy you need during the day? Well, the net energy loss over a day is going to be this number times 86,400 seconds. Big number. All right. And we can drop some zeros. Oh, I've done something weird here. I'm sorry. Please excuse me a minute. Let me check my math. 1 moment, please. Okay, I found my problem. And after we pause... Alright. So, the power at 293 is 585 watts. So the net power is 148 watts. So our net heat is 148 times 86,400 watts in seconds. Much more tractable number, right? Is I'll cover that, it goes out. So 148 times 86,400. All right, so first off is we can convert this to calories. So we divide by 4.186 to go from joules to calories. And then we divide by 1,000 to go from calories to kilocalories. And what we get is that Q is about 3,000 calories. So just the mere existence at 37 degrees Celsius requires 3,000 calories a day. If these numbers are true. They're not true. One is we took this E equals 1. So if we actually take it to be like 0.6, then That's about 1,800 calories. That sounds more like what your doctor tells you. If you actually go talk to them, they'll tell you even less is fine, depending on what you're doing. All right, a relatively healthy person, the government used to suggest something like 2,000 or 2,400 calories. All right, and of course this emissivity varies, so the net power is going to change, and this is an estimate. Right, all of this is an estimate. But ballpark, you can kind of see the picture here is just existing, you lose energy. And so you have to replace it to stay warm and to be able to do other stuff. So you have to eat your Wheaties in the morning. So that pretty much wraps up everything. But I will take a moment and let you see the most adorable friend of mine. This is Frances. That blanket she's on is a heating pad, and she loves that thing. She's about 14 or 15 years old, and she is my baby. Right. And we transition. I don't have a good I'm learning new software for this. My buddy Spike that was here, he's waking up and getting a snack. It's almost 4 in the morning, so we're going to let the video stop here. One more look at my sweet little baby Frances. Ain't she adorable? So hopefully I'll see you guys on Monday.